Hello friends, here in this video we will see a problem on design of bolts in which the load is perpendicular to the bolt axis, and for that purpose here we have a question. For supporting a crane in a workshop, the brackets are fixed on steel column as shown in figure. Diagram is given. The maximum load is 12 kN acting vertically downward. The vertical face of the bracket is secured to the column by means of 4 bolts, 2 bolts in each row. Determine the size of bolts if permissible tensile stress is 84 megapascal. Also find cross section of the arm of bracket which is rectangular. Now this is the question which we have. Whatever is given in this question, I will write that in the form of data first. So let us get started. So in data, the first thing we should write is the type of the problem. And here the type is load is perpendicular to the bolt axis. Next, for supporting a crane in a workshop, the brackets are fixed to steel column. Here if we can see in this diagram, this is a bracket. Which is fixed to a steel column here. Next, as shown in figure, diagram is there. Maximum load is 12 kN. So W is equal to 12 kN. So it is 12 into 10 raised to 3 Newton. Then it is acting vertically downward as shown in figure. The vertical face of the bracket is secured to the column by means of 4 bolts. Now here as we can see, there is one section given. I can call it as section 1-1, and here this will be section 2-2. So at section 1 there are 2 bolts. One bolt is here and the other bolt would be behind. Similarly at section 2 there is one bolt here, other bolt would be behind. So each row has 2 bolts, it is given 2 bolts in each row. So in total we have 4 bolts. So therefore N, that is number of bolts, is 4. Next, determine the size of bolts. So the question is, we have to find out how much is the core diameter of the bolt, how much is the nominal diameter of the bolt, that is the outer diameter. Then if the permissible tensile stress is 84 megapascal, sigma T value, it is 84 Newton per mm square. Megapascal can be directly written in terms of Newton per mm square. Now also find cross section of the arm of bracket which is rectangular, and the next thing is we have to calculate how much is the width and thickness for the cross section of the bracket which is rectangular in cross section. Next, they have given the distances. I'll write the values. 50 mm, it is L1. Next, 375 mm, where the second section is there, it will be L2. Then 400 mm is the length of this load from the steel column. So capital L is equal to 400 mm. Now this is the question we have in front of us. Let us try to get the solution for this problem. Now in solution part, if we can see, when the load is acting, load is perpendicular to the axis of the bolt. Now in this case, when the bracket would be moved down, that is when the load acts, there are chances of this bracket to slide down, and when it is sliding, all the 4 bolts will get sheared off. So the primary effect is of shear. So we can say that in solution, first of all, since the bolts are subjected to 2 kinds of load. The first one is called as primary shear load. Second one, it is secondary tensile load. Now, when I am talking about the primary shear load, this load 12 kilonewton would be shared equally by 2 bolts in row 1, 2 bolts in row 2, that is 4 bolts. So therefore, primary shear load W suffix S is equal to capital W by N. So therefore W suffix S is equal to capital W is 12 into 10 raised to 3 divided by 4 bolts, it is given in the problem. So therefore I am getting the value of primary shear load as 3 into 10 raised to 3 Newton. I'll keep this as equation number 1. Next, after getting the primary shear load, the next thing is, suppose when the load is acting on the bracket, instead of directly sliding, there are chances of this bracket to tilt, and when it is tilting, the bolts which are closer to the load, they would be stressed more. Bolts which are far away from the load, they would be stressed less. Because of this unequal stretching, there are chances of the bolt to fail under tension, and that too, the bolts which are at section 2 will fail more or more heavily loaded because they are closer to the load. So here I can say that let small w be the intensity or load per unit distance, that is in terms of Newton per mm. Now therefore W, the formula we know, it is capital W into L upon 2 into L1 square plus L2 square. So here if I put the values, capital W is 12 into 10 raised to 3, L is 400, 2 into L1, it was 50 square plus L2 375 square. So therefore small w value, this comes out to be 16.768 Newton per mm. Now it is clear that on 1 mm length there is a load of 16.768 Newton, and this length is measured with respect to the edge at the bottom, which is called as the tilting edge AA. Now from this tilting edge, if I want to find out which of the loads are more heavily loaded, then it depends on their distances. The load which is most far away from this AA edge, that would be heavily loaded, and the bolts which are closer to the tilting edge, they would be less loaded. So we need to design those bolts which are heavily loaded. So they are at distance L2. So after this I'll say that therefore secondary tensile load W suffix T is equal to small w multiplied by L2. So hence W suffix T is equal to 16.768 multiplied by L2 is 375. So I get the value of secondary tensile load as 6.29 into 10 raised to 3 Newton. I'll keep this as equation number 2. Now, after getting the secondary tensile load, in equation 1 we were getting the shear load. So we cannot add these two values directly. So we have to find out the equivalent value. Therefore, equivalent tensile load, that will be W suffix T equivalent is equal to half of into bracket WT plus under root W suffix T square plus 4 into W suffix S whole square. Therefore, WT equivalent is equal to half of WT, the value we have got just now in equation 2, it was 6.29 into 10 raised to 3 plus square root WT 6.29 into 10 raised to 3 square plus 4 into WS, the value was in equation number 1, it was 3 into 10 raised to 3 Newton. So 3 into 10 raised to 3 whole square. So from this I will be getting the value of equivalent tensile load, and my answer is, it comes out to be 7.49 into 10 raised to 3 Newton. Now for designing the bolts we would be using this value of load, and as we know bolts they have threaded section, so we have to design the threaded portion of the bolt, because once you know the dimension of the threads, the other dimensions are very easy to calculate. So here I am drawing just the threaded portion of the bolts. Now this DC is the core diameter and DO is the nominal or outer diameter of the bolt. So as we can see, out of DO and DC value is less, so the thread, it will fail along the less diameter, which will give us the less amount of area. So here if I draw the cross section, this is the core diameter and this indicates the resisting area of the threads. So now I can say that this WT equivalent tensile load will be equal to area multiplied by tensile stress. I'll write it onto the next page. So therefore WT equivalent becomes, area is pi by 4 into DC square. Tensile stress, it is given in the problem as 84. Now we need to calculate DC here. So first I'll put the value of WT equivalent, 7.49 into 10 raised to 3 is equal to pi by 4 DC square multiplied by 84. So therefore we want DC, I'll keep DC square on one side, shift all the terms on the other side. So here I'll get the answer of DC square, which is 113.53, and here we need to calculate DC, that is the core diameter, so we have to take square root of this answer. So DC comes out to be 10.65 mm, our first answer. Next we can say that since DO, which is the nominal diameter, it is core diameter by 0.84, so therefore DO is equal to, core diameter is 10.65 divided by 0.84, so nominal diameter comes out to be 12.69 mm. Now we can round off this value up to 14 mm, so we can say that therefore selecting from course series threads M14, that would be the size of the bolt, M14 size of bolts. So this is the second answer for us. It means we need to use a bolt having outer diameter 14, core diameter would be 10.65 mm. Now after this, the last part of the question, they were also telling us to get the cross section area of the bracket. So here it was given that the cross section is rectangle, so I am drawing a rectangle here. Here we have the thickness of the rectangular cross section, and this is the width of the rectangular cross section. Now see, what can happen is that when the load is acting, there are chances of this bracket to bend. So we would be designing the bracket considering bending action. So I'll say that first of all, since bending moment M, it is equal to load, which is 12 into 10 raised to 3 multiplied by distance, which is 400. I am taking the moment of load into the distance. So we are designing the bracket section at distance 400 mm. So therefore M comes out to be 4.8 into 10 raised to 6 Newton mm. Now after getting M, we need to know the section modulus. So I'll say that since section modulus Z is equal to I upon Y. Here I'll write down the value. I is about Ixx, that is TB cube by 12. Y, it will be equal to B by 2. So I upon Y, that will give me Z is equal to TB square by 6. So I'll use this value. Z I can calculate directly as TB square by 6. Now in this problem, the relation between thickness and width, they are not given. I'll assuming B is equal to 3 times of T. So therefore I will get Z as, I'll replace B by 3T square divided by 6. So finally here I will get this as, this would be Z is equal to 9 T square by 6. So after this we can say that therefore this will be 9T cube. Actually this is T square into T. So 9T cube by 6. So finally I can say that therefore bending stress sigma B is equal to M upon Z. Now bending stress is not given in the problem, but bending and tensile stresses, they are considered as principal stresses. So instead of bending I can take tensile stress. Bending moment value was 4.8 into 10 raised to 6. Section modulus, it is 9 T cube divided by 6. So therefore sigma T value, it is given in the question, it was 84 is equal to 6 will go into the numerator, 6 into 4.8 into 10 raised to 6 by 9 T cube. So therefore here after getting this we would be shifting T cube on the one side. So T cube will be shifted on one side. Here I have 6 into 4.8 into 10 raised to 6. In the denominator we have 84 into 9. So now here I will be getting the value of T cube, which comes out to be 38.095 into 10 raised to 3. And here we don't want T cube, we want the value of T. So taking the cube root of this answer, my value of T is 33.65 mm, which I can round it off to 34 mm. Our third answer. Then at last I can say that since B is equal to 3T, the relation we have assumed, so therefore B will be equal to 3 into thickness is 34. So finally I will be getting the answer of B as 102 mm. This is the fourth answer. So here we have designed the cross section of the bracket, and if we look into the question, here They were telling us to calculate DC and DO. We have found out the values. DC was 10.65 mm, DO 14 mm, T we have got it as 34 mm, and B it is 102 mm. It means here for the bracket which was given, we have designed the size of the bolts by DC and DO. Next, we have designed the cross section. They were telling us to find, first of all, determine the size of bolts that we have got. Next, find the cross section of the arm. The cross section of the arm means by B and T value. So we have defined, or we have found out the values of B and T. It means here we would be having the cross section as, this is the cross section which is rectangular for the given bracket. Your T is equal to 34 mm and B it is equal to 102 mm. That is, we have designed the cross section of the bracket. This is cross section of the bracket, and with this we complete the problem.